Now, today's lecture is going to be on the approximation methods in numerical analysis. Now, approximation methods basically start from the situation where you have some function, f of x, which you find difficult to compute, maybe extremely costly to compute for each individual x. So what you want to do is to replace it with a simpler function, a cheaper to compute function that approximates f of x. Now, the questions that you have to address is first, what data should be used? Now, you see the data here is going to be evaluations of f of x at a finite set of points x. Well, which points should you choose? Where should you evaluate f of x? Now then, how should you use them? How should you take that information and construct some g of x? So what family of simpler functions should you use for your g of x? Now, another thing which is ignored in economics generally is what notion of approximation do we use? Economists are familiar with L2 approximations. That's what regression is. They're also familiar with L infinity approximations, but those are just approximations of f. Sometimes we want to approximate both f and f prime, maybe even f double prime. And now one needs to know what kind of approximation do you need for the purposes of the approximation. So now, how good can the approximation be? How simple can it be? Those are all questions that you're going to have to ask if you're going to do some approximation. Now, many of the approximation methods that we'll talk about today look like statistical regressions. Both have an unknown function. Both use a finite amount of data. Here's the big difference. Statistical data that you use, let's say in empirical work, is noisy. Sorry. We are going to, however, assume here, or the approximation theory I'm going to be telling you about, assumes that the data errors are very small, that you can compute f of x at a finite number of x's and you can do so to high accuracy. Now, the other thing about empirical work is that you don't get to choose the kind of data you have. I often say that Mother Nature is a bitch because she will not only give you noisy data, but she might give you a lot of it where you don't really want it and not give you much of it in the part of your space that you really are interested in. So you really have lost a lot of control here. Now, with numerical approximation methods, we get to choose the x's at which we compute f. We get to choose how to fit them. And also, many of the approximation methods are more like experimental design ideas from statistics and with very small experimental errors. So there are going to be many similarities with regression, but there are going to be very important differences. And we'll see them as we proceed. Now, the first type of method are local approximation methods. Now, the general approach for local approximation method is that you use the information about a function. Let's say we're just talking about scalar functions now. but you use information about f only at a single point to construct an approximation that is valid for other points nearby. Now, the canonical example of this, the simple example of this, is, of course, Taylor series approximation. If you have some x naught, you compute f of x naught, and then you also compute f prime at x naught, f double prime, etc. And from that information, you can construct a degree n polynomial. And its error is going to be on the order of the n plus 1 power of the distance between x and x naught. So that's Taylor series approximation. And now it's going to be accurate in some range of x's around x naught, but we'll have to see, we'll see later how good it is. Now, related to that is the notion of a power series. Now, a power series is an infinite sum. It's an infinite degree polynomial, essentially. Now, a power, when you plug in some value for z here, that infinite sum may converge or it may diverge. You know, depends on the character of the a sub n coefficients. Now, the radius of convergence. Now, so you think of basically what we're talking about here is the situation where 0 is the center of the universe, and what you care about is how. Now, by the way, if you have a function, you know, if you plug in z equals 0, then what's going to come out here is a0, and let's say hopefully that is so that's a0. Now, so at z equals 0, this converges. Now, the question is, for how many other z's around 0 will this converge? So we define little r, radius of convergence, to be the maximum magnitude of all the z's such that the magnitude of the infinite sum is finite. So this is a definition. The radius of convergence is some little r, which is defined by being the supremum of the magnitude of all z's such that the power series converges. Now, that's a definition. Now, then you might ask, well, why is that an interesting definition? Okay, the hazards of lecturing from home. We'll just let that ring. So now the problem here is that you could think of some function such that, oh, it converges for some points around 0, but then it doesn't converge until you get to some other big point at 100, and you might wonder, well, why is this radius of convergence valid or interesting? Well, here's the theorem. The series converge, basically, you take that little r, the series will converge for all z's of lower magnitude, and will diverge for all z's of greater magnitude. So this basically, this little r divides the entire space into 3 regions, where the magnitude of z is less than r, where the magnitude of z is bigger than r. Of course, then there is this region where the magnitude of z equals r. Notice that this theorem doesn't say anything about that. And in fact, the behavior at z equals r can be viewed as being random, or it's not, nothing is said here. But what this says is that if the radius of convergence is r, then this infinite series will converge for all z's of smaller magnitude. Now, I should point out something here before I proceed, that when I talk about z's, now remember this, the function I'm talking about, f of x, I initially said it's mapping from r to r. Well, actually, I'm really thinking of f as being a function from the complex plane to the complex plane. So now within the complex plane, this is still a one-dimensional function. So we're ignoring the two-dimensional structure of the complex plane. And then everything I said before about power series and everything is still valid. Now, so in order to talk about radius of convergence and understand it properly, we have to realize that we have to think about it in the complex plane. Now, a function, complex valued function from complex numbers, is called analytic on some domain omega, if and only if for all points in that omega, for every point A, there is some little r, some sequence ck, such that this infinite series does converge for all z's within r, distance r of A. Okay, so basically, you take a point in omega, and then you say, is there some, by the way, there exists an r bigger than 0, is there some non-trivial ball around it such that the power series converges? So that's the definition of an analytic function. An analytic function is kind of like an infinite order polynomial. It is when it exists and when it's well formed. Now there's going to be some points, there are some functions such that at some points, let's say maybe even at A, where things aren't going to work out right. For example, log of x. Well, log of x is analytic for every point except where x equals 0. And by 0, I mean in the complex plane. So a singularity of f can be an analytic function on some domain on omega minus the point A, but not on omega. Now, singularity in general is going to be some point where either f itself, like log of z, is not analytic, or maybe some derivative of f has a singularity. Now, if there's a singularity at z and you're sitting at some fixed z, then this power series, basically a Taylor series based at x0, is going to be bounded above by the distance between x0 and z. So basically, if you know where a singularity is, and here's an example. If you know where a singularity is, you know the radius, you have an upper bound for the radius of convergence. Now think about the function f of x equals x to the alpha, which is for real numbers, real positive numbers, like our production functions typically are. There is a singularity at x equals 0. The radius of convergence for power series, therefore, around x equals 1 is 1. So if you're sitting at x and you construct a Taylor series or to the infinite order, that power series will converge only in the points z that's within distance 1 of 1. Because it can't converge at x equals 0. And so what this also says, by the way, is that this power series is not going to converge, the infinite order Taylor series is not going to converge at x equals 3, even though f of x is defined for every point between 1 and 3. The Taylor series around 1 is not going to be convergent at x equals 3. And that's because of the singularity at 0. So this may seem strange, but this is the way the math goes. Now, and I show this here. So suppose you have, suppose you did a Taylor series approximation and of order n, and you did it, it's basically at 1, it's going to be exact. And then you look at the error at other points. Now you see that for 1.2, so this is like, remember, we're basing the Taylor series around 1. So this says that as we increase the order of the polynomial, the accuracy at 1.2 goes to 0. It's very good approximation. The same is true on the other side at 0.8. However, if you're looking at the accuracy of the Taylor series based at x equals 1, and you're looking at how well it does at 0.5, you see that there also is a progression, but it takes longer to get really good 12-digit accuracy. Now, if you're at 0.05, you see that the validity of the Taylor series is still there, and probably will be there asymptotically, but you only got 3-digit accuracy even at the 50th order. Now, 1.8 is kind of like 0.2, and so its convergence is slow. Now, at 2, this is a critical point here, because 2 is not inside the radius of convergence. Radius of convergence is 1. 2 is not inside the radius of convergence. However, it's not outside. And it appears that it's going to work out fine, but again, only for higher orders. Now at x equals 3, this is definitely outside the radius of convergence. And what you see is that this, as you increase the order of the Taylor series approximation around x equals 1, the validity gets worse and worse and worse at x equals 3. So this is the nature of Taylor series approximations. You've got to know, you've got to understand the function from a complex plane point of view. Think about where are its singularities in the complex plane, and then that tells you about something about the possible radius of convergence. And by the way, this is, we'll see later, this is very relevant if you're talking about taking perturbation methods to higher order perturbation methods in a dynamic model. Now, those are basically just computing a Taylor series approximation around a steady state typically. And so you've got to worry about the radius of convergence and the radius over which, the region over which the approximation is accurate. So this is important stuff to have any idea about whether or not your approximations work. Now, there's another way in which you can use information at a function f to construct an approximation. So the idea of a Padé approximation is that the approximating function is going to be a rational function. Rational functions are ones where you have a polynomial divided by a polynomial. And what you do is you choose the coefficients of these polynomials, p and q, so that the derivatives of this rational function match the derivatives of f at some x naught. Now, typically what we do is we have the polynomial, I think, p is degree m and q is n, and then you either have them typically of equal degree, or the numerator being a bit one order higher degree. And then the coefficients of p and the coefficients of q. Now remember, if p is an m plus 1, if p is an m degree polynomial, then there's m plus 1 coefficients. And n and q is an n degree polynomial, there's n plus 1 coefficients. Now you must have them satisfy these conditions that the kth base, this is basically just, you want this rational function that basically equal f, and so that's why then it's going to be p here is going to be roughly the same as f times q, but now the kth derivative of p has to be equal to the kth derivative of f times q. Now And so this, you go up to order m plus n. So there's m plus n plus 1 conditions here. Now you might say I'm missing one, but you can, by normalization, just say that the summation of the coefficients for q has to equal 1 or some normalizing thing. Because remember, you can take, if you have two polynomials p and q and you multiply the coefficients of all of them, if you double all of the coefficients, you're not going to change the rational function. So you have a normalization condition that you typically use. Now, by the way, this system may be singular, which means there are multiple solutions. And so then what you do is you reduce the order of the polynomials that you're looking for to the point where you get a singular system. So basically, if this is a singular system, then what you want to do is basically just find the rational function of minimal polynomial degrees that solves this linear system of equations. And so here's an example of a Pade approximation of x to the 1/4 power based at x equals 1. We go through the steps and we find out that this is the approximation. Now, Pade approximation is often better because it doesn't have this singularity. Its radius of convergence is not affected by the the singular points of the underlying function. Now, many of you are familiar with log linearization. So suppose we have some function of x and epsilon where you're trying to define x in terms of epsilon. And so you do implicit differentiation. And then the way we do it in economics is talk about x hat is equal to dx over x. And then, well, that turns out to just be equal to, by implicit differentiation, equal to this expression. I think I might, oh yeah, okay. Which equals this, and this should be epsilon hat. Sorry. So basically x hat here equals this expression times epsilon hat. So this is your hat calculus, as many people would call it. Now, what that means is that we can write out an approximation of the x function in terms of the log of x minus log of x naught equals this expression times log of epsilon minus log of epsilon naught. And then, of course, that means that when we exponentiate everything, we have this approximation for the function. So log linearization is also what's called the hat calculus. But basically, it's just an example of a nonlinear change of variables. That's all log linearization is a nonlinear change of variables. Now, in general, suppose you have some function, cap y, as a function of cap x, implicitly defined by this equation. However, we would, for some reason, want to express this in terms of the log of x and the log of y. And then, of course, and so what that means, of course, is that little y of x equals log of big Y evaluated at e to the x. Now, so this is the definition of y to the yx, little yx. And that definition tells you that y prime is equal to d log x, log y over log x. Now then, by replacing the y of x definition, by replacing y of x with the log of y of x, we see that this expression is equivalent to this expression. And so now let's say that what we're trying to do is find some approximation so that then this g of little y of x comma x is equal to 0. Now we implicitly differentiate the g function, or actually this function, at some point, let's say x at some x naught, and you will get the value of y prime at that x naught. But you also, but that y prime at x naught has to be compatible with this definition of y prime. And so what you find is that little y of x, which is log of y of x, equals little y of x, is equal to, approximately equal to little y of x naught plus y prime times x minus x naught, which is a linear approximation of the log function. And then if you want a first order approximation, the corresponding first order approximation, you just do a exponentiate both sides. Now, by the way, you can use, when you approach this as a general nonlinear change of variables, you can start thinking in terms of second order approximations. So you could think not just in terms of log linearization, you could think in terms of log quadraticization. You know, it's all log linearization is just a special case of nonlinear change of variables and then applying Taylor's theorem. You can also use it to construct a Padé expansion in the log. There's nothing special about the log function. You could take any monotonic h of x function and go through these methods and get an approximation. And I have a paper actually which does some Taylor perturbation methods around a steady state and shows that log is nice, but there are other things that can be better. Now that's, okay, so I spent a little time on Padé and nonlinear change of variables, just to point out to you that these are alternative approaches to approximations. Now, for the rest of this lecture, I'm just going to talk about sort of standard things like regression, but they're going to be global now. Now, for global approximation, what you want to do is gather information about this unknown function at a variety of points x and over a wide range. So, and then compute some approximation which is good over that range. Now, one way to go is what's called interpolation. And so you construct a set of data. What you want to do is pick some x naught and then pick some y naught, which equals your f of x and y xi's, and then yi's are going to equal your f of xi's. And then you find a polynomial of degree n minus 1. We're going to call it Pn. The subscript n here refers to the number of points used, which agrees with the data. That is that the yi's equals the f of xi equals the pi. I changed that. I should actually make use of the annotation tool for my own future notes. There. Now, if the points are distinct, then there's a unique interpolating polynomial. Because it's just, if the xi's are unique, are distinct, then this is just going to be n equations and n unknowns. No. I just got to turn off the. Oh, this is what happens when you're trying to do something fancy.
You need to click the red cross on the right, but clear it first, because it's going to stay on your screen and not on your PDF file.
Here? No.
There should be a red cross at the right.
On the right. Okay, I think I fixed it. That's not so good.
So if you go back to annotate, then you can either erase or clear it.
Yeah, okay, so I need to, I need to go to, annotate, and then I want to clear everything?
Yeah.
Okay, thanks. Okay. Okay, I think I'm back in control now, yeah. Thank you. Okay, so interpolation is one where you take n points of the information about points, f at n points, and then you fit and see if it does a good job. Well, it doesn't always do a good job. And so here I'm going to show you one of those Mathematica notebooks. And this is called Runge's phenomenon. So now, suppose we have, so here's Runge's function. 1 over 1, let me see, yeah. It's 1 over 1 plus 25x squared. Why did I put the 25 in here? It's convenient. Because then between -1 and 1, we get this red curve. Now that looks like a relatively nicely behaved function. Now, suppose, however, we do interpolation at 5 equally spaced functions. So here we take 5 uniformly spaced functions, x equals -1, 1/2, 0, 1/2, and 1. So we take f at those points and then compute a degree 4 polynomial, and we end up with a degree 4 polynomial approximation. Now that doesn't really look like a very good approximation, and it's not. So you might say, well, what you should do is use more points and a more flexible polynomial. So let's bump it up to 10. Well, okay, that looks like it's getting better. Let's bump it up to 15. Well, that's looking nice in here, but it's not doing so well out here. But maybe by just throwing more points in higher order degree polynomial, well, no, that doesn't work. I mean, basically what's happening is as you increase the number of points, you're going to get a better and better approximation within this range, which is roughly -0.6 to 0.6, something like that. But it's going to get increasingly worse outside. And so what happens is that it's very good in here, but then the errors explode into the hundreds of thousands in this outer region. So the idea of taking n points and fitting a degree n-1 polynomial to that looks bad. Now, so you might conclude that interpolation, of course, is going to be a bad idea, because from a regression point of view, how many degrees of freedom do you have? You have n data points and n unknown coefficients. Well, the degrees of freedom is 0. And so as you should know from your statistics courses, that's not a good approach. That's not good. You need to over-identify the condition. So you might think that interpolation is just a ridiculous idea. We'll come back to that. So, this is, oh yeah, there's a little bit, okay. My function had it between -5 and 5, on 1 over 1 plus x squared, but the CDF file had it 1 over 1 plus 25x squared on -1, 1. Now, by the way, is there some singularity messing things up here? Suppose we were to write a Taylor series approximation. Would that be better? Is there a singularity in this function? Well, this function is well defined for all real points x. However, there are 2 singularities nearby. Think about x equals I or -I, whereby I mean the square root of -1. Well, if x equals I or -I, then this is going to be 1 over 1 plus -1, which is 0. So there is a singularity close to x equals 0 in that sense. So that starts to tell you something about how, well, this function might present challenges for approximation purposes. Now, let me now describe some other kinds of ideas. There's Hermite polynomial approximation. This is where the data you gather include, you choose xi's, and then you compute the yi and the yi prime. So you compute yi is f of xi and yi prime is f prime. Now you have 2n data information, points of information. So you try to find a degree 2n minus 1 polynomial, which agrees with the data. By agreeing with the data, it means that you want the yi's to be equal to the polynomial at xi and the derivatives also to agree. Now again, if the xi's are distinct, there's going to be a unique solution to that. Now one could go on and on like this. You could have, I don't know what it's called, but you could have look at a variety of points xi and compute the first, second, and third derivatives and then interpolate on that. So the interpolation idea is not limited to just using the values of f. Now Hermite interpolation probably doesn't have much of an analog in regression. So this is an example of where the numerical method does go beyond in an interesting way what you do from standard statistics. Least squares approximation. Now this is the functional version of regression. Suppose you have a function f of x. The least squares, and then you have some family of functions, capital G. A least squares approximation in capital G is that little g. Boy, that's messed up. That should be min. Sorry. That minimizes the sum of, minimizes the L2 norm of the difference between the two functions. So you have these two functions over some range, and then take their absolute value, square it, and then compute a norm. And you want to minimize that L2 norm, essentially. And that's least squares approximation in a functional domain. Now, okay, so now, what I'm now going to do is, again, describe to you some terminology. A lot of this lecture is just going to be sort of teaching you the language. Now, we often like to use orthogonal polynomials. Now, remember that in regression, you would love to have regressors that are orthogonal. That's very nice to have orthogonal regressors, because then regression is easy. The same is true if you're trying to do least squares approximations of functions in a function domain or in a space of functions. So now, what is an orthogonal polynomial? Okay, suppose you are operating in some domain D. You have some weight function that's strictly positive over that domain. And now let's define, once you have the domain described and the weighting function determined, then you can define an inner product. The inner product between f and g is nothing more than the integral over the domain D of f times g times w. Now, for some of you may have seen this notation where you called it the bracket notation, and there's a lot of similarities there. So this is the inner product. This is the definition of an inner product. Now, by the way, notice that this inner product looks a bit like a covariation between two functions f and g. And in fact, it really is the analog of covariation. Now, here's a definite, that would define the inner product. We define now this concept. Phi I is a family of orthogonal polynomials with respect to Wx over the domain D, if and only if the inner product is 0 for any two distinct members of that family. Now, I'm going to just tell you as a fact that orthogonal polynomials, once you define them, can be computed in a recursive fashion. By the way, the first orthogonal polynomial is always going to be 1, you know, or some constant, not 0, but some non-zero constant. And then the second function you throw in is typically going to be x, or some linear function. And then after that, the k plus 1 orthogonal polynomial in a family can be defined recursively in this manner for some coefficients a, b, and c. Now assume that the norms, oh, by the way, okay, the norm of phi I is the inner product with itself. Okay, so which is in a vector space context, what you think of as a norm. Once you have an inner product, the norm of an element in a vector space is the inner product of an element with respect to itself. Now, assume that for every I, the norm of phi I is 1. Now, that is actually what we call an orthonormal basis. In that case, you can decompose a function as a infinite sum where the little ai's are defined here. Basically, the little ai's are nothing more than the inner product of f with respect to phi I. And here's the inner product written out more carefully. Basically, little ai is nothing more than the covariation of f with phi I. So basically, this regression just projects each f function into the phi I dimension, and you get out the coefficient ai. So notice, this is exactly what happens if you're doing regressions, and all the regressors, all your data is orthogonal, all your regressors are orthogonal to each other, then the regression coefficient, any regression coefficient is nothing more than the covariance of a regressor against the data. So this is just like statistics. Now, what are some orthogonal polynomials that we use? Well, you might think that the one natural thing to begin with is, well, suppose that we have an interval -1 to 1. And we put the uniform weight function on there. I mean, what could be simpler or more natural? And then in that case, one can prove that the Legendre polynomial is defined in this fashion. Now notice that it's kind of ugly, but it is a polynomial. You have to take this quadratic polynomial, raise it to the nth power, and then take its nth derivative. And well, anyway, that's how you get the degree n Legendre polynomial. Now, you never want to use this formula to compute the Legendre polynomial. This expression comes from some motivation in physics. By the way, all of this stuff comes from physics, the mathematical physics. Here's the recurrence formula. P0, the zero order polynomial will be 1. The degree 1 orthogonal polynomial will be x. And then after that, you can just compute each successive orthogonal polynomial by a simple combination of the previous 2 orthogonal polynomials. So if you're going to compute, let's say, the first 10 orthogonal polynomials, this is the way you do it. At any point x, you do this recursion. So computing these is not expensive. Now here comes something that looks a little bit stranger. You again use the interval -1, 1. But now the weight function is going to be the 1 over the square root of 1 minus x squared. Now, you might wonder, where did I get that from? We'll see later where that came from. And then what is the formula for the orthogonal polynomials? Well, it's cosine of n times the inverse cosine of x. Now, at first, that doesn't look like a polynomial. And in fact, that expression is not a polynomial expression. However, it is equal to some polynomials. And here's the recurrence formula for the Chebyshev polynomials. By the way, it's called Chebyshev polynomial, but the letter T is used. And that's because in some Western Europe languages, Chebyshev is spelled T-C-H. You know, basically transcribing or translating Russian names into Latin alphabet names is difficult, and so the use of the letter T reflects the fact that I forget which language, I think it's French, spells Chebyshev with a T. But for some reason, I think we also spell Chebyshev now today with a C. So this is not confusing once you know a little history. Now, another set of polynomials is Laguerre, where now you're trying to approximate functions over the half-infinite interval, 0, infinity. The weight is e to the minus x. Now, by the way, this should start striking up some interest on your part because, gee, doesn't this look like a lot like e to the minus rho t? If x is equal to rho t, where rho is a rate of time preference and t is time, well, then that's the weight function you have in computing present value of cash flows. So that's where you're going to see this used. So the weight function is the exponential. And here's the one definition, again, comes from physics. Now, again, it doesn't look like a polynomial, but it is. And here's the regression. Or here's the polynomial form that equals the Laguerre polynomials. And now for you finance geeks, you of course love e to the minus x squared, the kernel of the Gaussian density, and you like to look at, let's say, minus infinity to infinity. You like to look at where situations where stock market returns are practically infinite, or as is more the current experience, minus infinity. So you like to look at functions over that big range. And so then now you're into Hermite polynomial territory. And the official definition of a Hermite polynomial is this, but which obviously isn't the polynomial expression, but the recurrence formula here does show you will generate the Hermite polynomials. Now, so far that's pretty easy. Here is where it gets nasty, is where you say, well, my model doesn't live on -1 to 1. How am I going to do it if let's say in a growth model, capital stock lives between 1 and 5? How useful is this? Well, it's very useful. You just got to do a linear change of variables. You've just got to map now by the way, so this any compact interval, A, B, you can map it into -1, 1 by this map. And then if you have orthogonal polynomials with respect to some weight function over -1, 1, then these functions are orthogonal over the AB interval with respect to this weight function, okay? So it's a matter of doing linear change of variables. Even though they're linear, this is where you're gonna get screwed up in using this stuff, is figuring out the linear change of variables and bouncing between one variable and the other, and that's where you're gonna get messed up. But the key thing is that I've shown you 2 ways to do orthogonal polynomials on -1, 1, and those ways can be used on any compact interval. I showed you how you can do orthogonal polynomials on 0, infinity, and that can be used for any half-infinite interval, a to infinity. And I've also shown you how to do -infinity to infinity, using a Gaussian kernel. And so again, if your problem lives on that domain, you can use a linear change of variables to create orthogonal polynomials in your domain. Now, those of you who have studied time series econometrics, and I'm not one of those people, will be familiar with trigonometric polynomials and Fourier series. Now, the key fact is that the functions cosine n theta and sine m theta, that whole set of functions, they are orthogonal. It's an orthogonal collection on -pi pi. Now, if you have a function that is continuous on -pi pi and it's periodic in the sense that f at the left interval, at the left point equals f at the right point, then this is a Fourier expansion of the function f of theta. The Fourier coefficients equal this, which is again basically nothing more than regressing f on the various trigonometric functions. And furthermore, the convergence of this approximation is uniform over -pi pi. But again, remember that this is only for periodic functions. So Fourier series are excellent if you want to approximate a smooth periodic function. The problem is that we don't typically deal with periodic functions. For example, the production function f of k. Let's say you have a small capital stock k equals 1. Let's say the big capital stock is k equals 100. Well, I think we agree that you don't want f of k to equal f of 100 if this is a production function, because production functions typically are monotone increasing. The more capital you have, the more output you're going to get. So our functions are typically not periodic. And if you try to apply Fourier series to these things aren't going to be working out well. However, it's the Fourier analysis, strengths of Fourier analysis, that is behind Chebyshev polynomial theory. Now, why is that? We'll go back to the definition of Chebyshev. Where do you think we got this strange looking function? 1 over the square root of 1 minus x squared. Well, now, if you put in x equals cosine theta, well, gee, 1 minus cosine squared is going to be sine squared. And then this is going to be basically sine of theta. I mean, or 1 over sine of theta. So this is where you start to see the connection between Chebyshev polynomials and Fourier series. And what happens basically is that the Chebyshev theory is nothing more than Fourier series theory translated to non-periodic functions as much as is possible. So that's the connection there. Now, I have dumped a lot of jargon on you right now. So this is also a time for my fizzy water break. Any questions or any lack of clarity on understanding on what these, what are the definitions and concepts behind these things I've been talking about? So just raise your hand or type in something on the chat. Okay, now let's continue then. Okay, now we're going to start talking about stuff that you're more familiar with, regression, where you have endpoints of data, and then you try to find some function with some free parameters beta. Yeah, here's your data. Here's your free parameters beta. And least squares regression is nothing more than trying to find some parameters. So this is like a functional form. So you're trying to compute f of some function f of x, and then the beta are the parameters, like the coefficients of a linear regression. So what you're trying to do is minimize over all the betas to choose the betas that minimizes the sum of squared errors. Now, Chebyshev regression is where you want to come up with a degree m polynomial. You pick n data points. N, of course, has to be bigger than n plus 1. That are the n zeros of the degree n Chebyshev polynomial adapted to coefficients a, b. And then you minimize the unweighted sum of errors at those nodes, those 0 points. Now, let me attend to a problem. So here's the definition of Chebyshev approximation. You have a function f, and you want to compute a degree n Chebyshev polynomial with m points. So then you have to translate the Chebyshev interpolation nodes, or the Chebyshev zeros on -1, 1. You translate them into your AB interval, which is this formula. These are the Chebyshev the zeros of the degree n Chebyshev polynomial. You adjust the nodes to the AB interval. That's here. You evaluate f at those nodes, and then it turns out that the sum of the least squares summation boils down to just a very simple formula that the coefficient of the degree I Chebyshev polynomial is nothing more than the covariance of the weight. You take the covariance of the, okay, these aren't weights, this is W, these are more like the Y's. You take the covariance of the Y's with the Chebyshev polynomials and divide by the variance of the Chebyshev polynomial. Again, it's nothing more than just regressing the data on each individual regressor. And then you end up with this approximation on the interval AB. Now, why do we talk so much about this? It turns out that Chebyshev regression, including interpolation, is very good. And here's the key theorem that says that the L infinity error between f and its degree n Chebyshev approximation is bounded above by these terms. And as I explain in the next slide, this term doesn't matter. This is independent of the function. This term is a measure of the kth order curvature. This is n to the minus k. And so you see how by increasing n, you can rapidly convert. For a fixed k, by increasing n, you can rapidly converge to the true function. So that's the nice feature of Chebyshev polynomials. Now let me show. Oh, I shouldn't have done that. Sorry. I'll open recent. So let's go back to the Runge problem. And what we find is that now in this CDF file, I can also do the Chebyshev points. Now the Chebyshev zeros are, here you see the Chebyshev zeros, five Chebyshev zeros, they're going to be located different. What's going to happen is that you're going to have this point, which is a little bit bigger than -1, corresponding to this point, a little bit less than 1. And of course, x equals 0 is going to be there. And then you're going to have these two numbers, which are closer to 1 than to 0. Now, that's nothing to write home about. But now let's increase the sample points up to 10. And what you see is that the Chebyshev zeros, the points at which you're using for the interpolation, seem to be concentrated more towards the end, not so much in the middle. And then go up more to, let's say, like 20. Boy, that looks nice. And down here, you see that the error is like 0.04 at most. And now, oh boy, this is looking good. And so what you, and at the max, 50, you see that the error is practically 0. And so now let's actually do the movie. So as you increase the number of points you use, the approximation gets better and better and better. So what's the point of this demonstration? The problem with interpolation that we saw before was not a problem with the interpolation idea. The problem was that we made a bad choice of points. We tried to interpolate on a uniform set of points. And that was in the Runge's counterexample, and that was the bad news. If we approximate on the Chebyshev zeros, then we get interpolation will give you excellent results. Now, in economics, a lot of times when people try to approximate functions, they don't pay attention to their sampling scheme. They might think, oh, I'll just take a uniform sample of points and then run some approximation on it. Well, the Runge phenomenon says that's not good. By the way, even if you did a regression approximation where you sort of did some over-identification, it's still not a good idea. The sample of the combination of, uniform points and polynomials is not a good approach. It's not a good scheme. The quality of an approximation depends greatly on the set of points at which you have data. And in numerical methods, you get to choose what x's are used in creating the data for your regressions or approximations. Now, the other thing is that you don't, in the case with the Chebyshev nodes, you notice that they tend to be not in the center, but they tend to be denser in the outer edges. Well, that's because you need more information in the outer edges. You see points on the interior. Let's say you look at the quality of an approximation at x equals 0.23. Well, it's probably got data points to the left and the right of it. So it's getting information from both sides. Whereas if you're a point out, let's say like 0.95, you probably only have information on points less than 0.95. So you need, in order to get quality approximations on the end regions and the edges, you need to sample there more intensely. And the absolute worst way to sample something is to take a random sampling of points and then find out, and particularly in dynamic stuff, where then that random sample probably is concentrated in the center, and then do an approximation. That's like the absolute worst possible thing to do. There may be some intuitive motivations for that. It's bad numerically. Now, let me finish off. Now, this, by the way, the label approximation, this lecture has a label of approximation 1. In a few weeks, I'll be talking about approximation 2, where I will talk about, let's say, much more modern approaches to approximation. What I've given you so far and will continue to give you today is sort of the classical ideas in approximation. Orthogonal polynomials, Chebyshev polynomials, interpolation, etc. Those are the classical ideas, and that, of course, those are the ideas that you see, of course, in my book and most of my writings. Certainly, I'd say anything I wrote in the previous millennium. But we're going to see more powerful, more modern methods later on when I do the next lecture on approximation. So now, I'll say a few words about multidimensional approximation methods. It's basically the same setup. You have data, you have x points in Rn, and you have some z points in Rm, and you have a function that's a function on n-dimensional Euclidean space, and the output's in m-dimensional, and you want to find, let's say you have this data, you want to find some function, polynomial, let's say, that matches the data. Now, things don't go so well. Suppose that you choose these 4 points, 1, 0, minus 1, 0, 0, 1, 0, minus 1. And you have data at these 4 points about a function, and you want to use it to compute the 4 coefficients to get an approximation using 1, x, y, and xy. Well, when you try to do that, you find out that the linear system equation for the coefficients is a singular, and actually there's no solution to this thing. So the placement, you have to have, it's even more critical in multidimensional cases that if you're going to do interpolation, you have to have a sort of compatible set of points and set of basis functions. I mean, that's what we're doing. We're talking about a space of functions, which is a vector space, and we generate arbitrary functions by taking linear combinations of the basis functions and then trying to choose the coefficients to match some data. And so it's in higher dimensions, even more critical that the geometry of the points be appropriately related and compatible with the basis functions of the approximation. And again, later I'll show you some ways to come up with good approximations in multiple dimensions. Now, when we go to multiple dimensions, the natural thing to do is to just take the one-dimensional stuff that you're familiar with and then just adapt it naturally to n dimensions. So now suppose that you have a set of basis functions over x, and then you have a collection of basis functions for functions over Rm, called functions over those y's. Now you want to do is create basis functions for functions that are products of the basis functions of the subbases a and b. And so this is called a tensor product. You take each phi in A and each psi in B and take their product. And that is your tensor product. Now suppose that all these spaces are the same. You can think of, let's say you have in dimension xi, you have the basis functions phi super I, and then the family is this family indexed by k. So that's the basis in dimension I. And then the n-fold tensor product for functions of n variables is just the collection of all products. Well, this is going to have a problem. You're going to have a problem with curse of dimensionality, and it's going to be bad. So this is going to be, now, by the way, you can do this tensor product approach even for multivariate functions. There, the weight in the multivariate domain is nothing more than the products of the weights. in one dimension, and your domain is just going to be the product, tensor product of the individual domains, and you have all these same formulas. But boy, this is going to be bad in terms of recursive dimensionality. This is the Chebyshev approximation algorithm in R2. Basically, it just does the same thing. You take the Chebyshev interpolation nodes at -1, 1. You have to adapt them for each interval. You evaluate at f at these nodes, and then the Chebyshev coefficients is nothing more than the values regressed against the products of the regressors, and it's all the same stuff. But you have a hideous recursive dimensionality. So if you have 4 functions, let's say you have cubic functions in each dimension. So that means you have 4 basis functions in each dimension. And now you want to go to 5 dimensions, then you have 1,000 basis functions. Now, suppose you want to go to 10 dimensions and you have 1,000,000, and suppose it just blows up badly on you. So if you're trying to do higher order approximations of functions in higher dimensions, you can't do tensor product. However, what we should do is go back to our reliable friend, the Taylor's theorem. By the way, Taylor's theorem has nothing to do with macroeconomics. So the Taylor's theorem for Rn produces an approximation. So if you have you're doing a Taylor series expansion around x0, well, that's going to be equal to f of x0, and then plus a combination of the univariate gradients. So this is the gradient of f in direction I, multiplied by the distance between xi and x0i. And so this is going to be a linear approximation. So for a linear approximation, you have n terms in your approximation. Now for your quadratic approximation, notice that Taylor's theorem just says that all you do is take the second order derivatives. All of the cross partials are going to be used, but only the cross partials. And that's, by the way, initially it looks like this is n squared terms, but no, that's n squared over 2 terms, because by symmetry, the cross partials are equal. So now you have n squared over 2 terms here. And so now the size of the space of polynomials, of complete polynomials in dimension n, grows algebraically in terms of the degree. So there is not a recursive dimensionality for this. That this may get to be big numbers, but it's not recursive dimensionality. So I and my collaborators have done problems where we have quadratic, even cubic approximations in problems with a couple hundred dimensions, and yeah, it adds up, but we're talking about the I don't know, maybe 5 digits as a number of basis elements, unknown coefficients. That we can handle. It's not, but we couldn't handle take dimension 200 and then a cubic in each dimension. That's going to blow up the tensor product version. So the key thing is that if you're going to do multivariate polynomial kind of approximations, Taylor's theorem says that all you need are what we call complete polynomials. So the degree k expansion of a Taylor polynomial uses a complete set of polynomials of total degree, where basically the polynomials of total degree k are all of the monomials such that the summation of the powers is bounded above by k. So let's say we do degree k in n dimensions. Here's the complete polynomial number of basis functions, and tensor product is 3 to the n. A cubic would have this number, which is roughly n cubed over 6, as opposed to 4 to the n. So you got drastically smoother, drastically fewer elements. This is kind of like if you take compare a square to a triangle. Let's say you take a square versus, let's say, a simplex. And what you see is that, geez, the simplex has half the area of the square. And we go to an n-dimensional simplex and an n-dimensional hypercube, you see that basically the n-dimensional simplex has the volume of it is like 1 over n factorial relative to the volume of an n-dimensional hypercube. So this is much better. And okay, good. So there are fancier ways of doing all of these things. We're going to talk later in the semester. We're going to talk about things like shape preserving approximation, constrained optimization methods for approximation. We're going to talk about neural nets. And by the way, there's nothing new about neural nets. There's a lot of new hype about them, but they've been around for a long time and well understood. It's now, though, that we have the software and hardware that can actually make good use of them. And I'll talk about neural nets later. Now, as far as software to implement these approximations, by the way, notice that everything I talked about today is a matter of solving linear equations or solving a quadratic solving a regression problem, which is just constructing some x prime x inverse x prime y thing. So they're all basic computational methods that you're familiar with. Now, I have not told you anything about splines. I'll talk about that later. One reason why is that the software that can compute spline approximations is the software out there is really a headache to use. But what I'm going to show you is some simpler constrained optimization approaches that will accomplish the same thing, and explain to you why the software out there is so hideous, but also not really appropriate for, not needed for us. So I haven't talked about splines, and there are some of these other and more advanced things I'll talk about. But this is what we call the classical approximation theory. This is what physics has given us, as the names will tell you. Names like Fourier and Hermite and Legendre. I mean, these are all people motivated by physical issues. But what I want to leave you with is that interpolation and regression are much like your statistics problems. You generate a finite amount of information and you use that information to fit a function. But the key thing is that you get to choose the points at which you generate data. And so that extra power that you have in your hands allows you to be much more efficient and in terms of constructing approximations of functions. But you have to remember that, what are you doing? You have to really keep in mind, okay, what is the domain I'm approximating a function, over which I'm approximating a function? What are the basis functions I'm using? What is the implicit norm I'm using? And then, is the set of points I'm using to generate the data compatible with the domain and this weight? I have seen people use Chebyshev polynomials, but in a manner which is totally ignorant of the whole package of behind Chebyshev theory, and so that's unfortunate. So So basically, the classical stuff gives you an idea of what is needed to get good approximations, and it's good base knowledge. But then we'll see later that we can go beyond that. Okay, I think this is the end of my official lecture comments.